Today we're going to be talking about graphing. So first, let's talk about some kinematic graphs. Usually, the independent variable is the horizontal axis, the x-axis, and the dependent variable is the y-axis. For this graph, it's a position versus time graph. So your x variable, which is your position, is on your y-axis, and your time is going to be on your horizontal x-axis. Time is almost always on the independent axis because it's normally your independent variable because everything depends on the time. One thing I want to point out very specifically is the trend line. You're going to be drawing trend lines on all of your graphs in your lab reports. So remember, a trend line is a best fit curve that passes as close as possible to the data points. You are not going to be connecting the dots, okay? So it's going to pass closely through a majority of the data points. Okay, Sally walks 4 meters in 2 seconds, stops for 1 second, then walks back 2 meters towards her starting point in 1 second. Draw a position time graph to illustrate this motion. It's already drawn for y'all, so let's talk about it while it's up here. First, we have to verify it's a position versus time graph. Time's on the x-axis, position is on the y-axis. And look, her starting point is going to be her y-intercept because that is going to be her starting position at time equals 0. She walks 4 meters in 2 seconds. So in 2 seconds, she walks 4 meters. That is a constant velocity, and she's moving in the positive direction, so the line is going in the positive position direction. She stops for 1 second. That's what this horizontal line means. When you have a horizontal line on a position graph, it means at 2 seconds, you're at 4 meters, and at 3 seconds, you're still at 4 meters. So you have not moved. You're stopped, you're stationary. Then she walks back 2 meters towards her starting point. Back toward her starting point. She changed her direction, okay? So now she goes 2 meters in 1 second. So from 3 to 4 seconds, she is moving back to 2 meters. And look at the slope of the line. It's now a negative slope line, so she's going to be moving in the negative direction. Now Sally walks 2 meters north in 1 second, stops for 1 second, then walks south 4 meters in 2 seconds. Here's the position versus time graph for that. Notice we have our 0 right here. So north is defined as our positive direction. Remember, that is up to y'all if you want north to be positive or south to be positive, but make sure it's clearly labeled like it is here. So we have our negative positions down here, south. She starts at a position of 0, 1 second, she walks 2 meters, she stops for 1 second again, then she walks 4 meters in 2 seconds back the other direction, and her ending position is -2. Now there's a lot of stuff we can tell from the position versus time graph. I can ask what your initial position was, 0. I can ask what your final position was, -2 meters. I can ask you what the total distance traveled is. She traveled 2 meters, then she traveled 4 meters. So her total distance traveled is 6 meters. I can also ask you what was her displacement. Final position minus initial position, so -2 minus 0, her displacement was -2 meters. Okay, so I got all of that from the position versus time graph. Here's how motion maps can correspond to them. The position of each dot on the motion diagram corresponds to the point on the position axis. Your first dot at time equals 0 says that this person is at 1 meter. So we start right here. That's our starting position at time equals 0. And we go so on. After 6 seconds, they're at 10 meters. So 10 meters in 6 seconds. The graph line combines information about the position of an object and the time when this position occurred. That's because the motion map can show you several things as well. The dots represent the position at that time, and the arrows can represent the distance traveled or the velocity in a given direction. The dependent variable is usually the y, and it depends on the value of the independent variable, which is normally your x. Y'all are very familiar with this formula, y equals mx plus b, but for physics we're going to use k for the slope. So k is the slope and b is the y-intercept. And again, on a position versus time graph, your y-intercept is going to be your initial starting position at time equals 0. So here's another thing you're going to be doing in your lab reports. You're going to have to find the equation of your best fit line. And what's important, you can't just use y equals kx plus b, you have to substitute your variables in. So for a position versus time graph, the value that's on my y-axis is my x position. So instead of y here, I have x here. My dependent variable is my time. Sorry, my independent variable is my time on the x-axis. So your x position depends on the time, and then the k is the slope, so whatever the slope represents in your graph is going to go there. The t for time is my independent variable, so instead of having an x here like I normally have, I now have a t here, and then b is my y-intercept. Okay, so you're going to have to interchange the variables that you're using in the graphs to represent the line for the equation for that line for that graph. Okay, this we've kind of already talked about. The slope of the line is the change in the dependent divided by the change in the independent. So we have x2 minus x1 divided by t2 minus t1 because my position is my dependent and my time is my independent. So that means the slope of this line is the change in distance over the change in time. That means the slope has units of meters per second. Does that sound familiar? What do we anticipate our slope being? The slope can be positive or negative. It represents not only how fast, but also in which direction the object is moving. Remember, positive and negative slope can be positive and negative direction. And b is the location of the object at time equals 0, the initial starting position. So, in case you were wondering, the slope of the line itself, just the magnitude without any direction, is the speed, how fast it's going. Then we look at the direction of the slope. Is it a positive slope? Is it a negative slope? That tells us the velocity of the objects because it now has a direction when we look at the positive or negative slope instead of just the magnitude of the slope. Okay, graphing constant velocity. There's going to be a ball that rolls across the screen, moving at a constant velocity. Look at the spacing of the little booms. Okay, that's kind of like a motion map. When you see equal spacing, it represents constant velocity. So here I have a position versus time graph. It has a constant slope, meaning it's moving the same amount of distance, the same amount of time. That translates into a constant velocity. So now this is a velocity versus time graph. It's a horizontal positive line because it has a constant velocity, and constant velocity is a velocity that does not change. So at 1 second, my velocity is 10 meters per second. At 3 seconds, my velocity is still at 10 meters per second. It's constant. The area under the curve for a velocity versus time graph is going to be your displacement. Okay, so this is a velocity versus time graph. We have a constant horizontal velocity, and if we found the area of this, that would give us the displacement, because our displacement, if we rearrange our velocity formula, we have velocity is displacement over time. We rearrange that, my displacement equals velocity times time. Well, that's my y value times my x value. My y value times my x value gives me the stuff underneath the graph, which is going to be my displacement. That's something that you're going to have to make sure and recognize. Anytime we do graphs, does the slope mean something? Does the area under the curve mean something? Okay? The position versus time graph. The slope is velocity. Now we have a velocity versus time graph, and we know the area under the velocity versus time graph is the displacement. So when we're graphing, make sure and look at the units, make sure and look at the axes, and see if the slope has a meaning or see if the area under the curve has a meaning. This is just something from the book that we liked the verbiage of. You can go back and read it on your own time. that's it. Yay, notes are done.